Have you ever just looked at the world and noticed how many different curves and shapes there are? I mean, from the way a ball flies through the air to the curve of a giant satellite dish. What if I told you that a lot of them share a secret identity? That there's a single, super elegant formula that's like a master shapeshifter behind the scenes? Well, today we're going to unlock that secret. Okay, so take a look at these graphs. At first glance, they have nothing in common, right? One shoots up in this perfect U shape, another one kind of twists through the middle, and a third one is literally split into two pieces. But here's the thing, they are all part of the same family. So the big question is, what's the family secret? The secret is hiding in a really powerful mathematical idea. But before we can just reveal the formula, we gotta understand the world it lives in, and that's the world of functions. Right. So before we meet our shapeshifter, we need to know the rules of the game. And the most basic rule, the bedrock of all of this beautiful math, is the idea of a function. So what even is a function? You can think of it like a super strict rule. For every single input you give it, we usually call that x, it gives you back exactly one and only one output, which we call y. There are no maybes, no sometimes this, sometimes that. It's always one input, one output. That's the deal. Yeah, the classic way to picture this is the function machine. Imagine this contraption where you drop an input number x into a slot at the top. Inside the machine, a specific rule gets applied. Maybe it squares the number, maybe it adds 3, whatever the rule is. And then, clunk, out comes one single unique output, y. It's totally predictable every single time. And, there's actually a really easy visual cheat to tell if a graph is a function. It's called the vertical line test. All you do is imagine sliding a perfectly vertical line across the graph from left to right. If that line never hits the curve in more than one spot at the same time, boom, it's a function. But if it touches the curve twice or more at any point, nope, not a function. It's as simple as that. All right, the rules are set. We know what a function is. So now it is time to meet the star of our show, the elegant, the powerful, and the surprisingly simple formula that's been hiding behind all those shapes we saw at the beginning. And here it is. This is the secret code. F of x equals k times x to the power of a. It looks so simple, doesn't it? I mean, it's just two little numbers, k and a, that are running the whole show. But don't let that fool you. This little formula is where all the magic comes from. So let's break down the ingredients, right? First, you've got k. Think of k like a volume knob or a stretch factor. It can stretch the graph vertically, making it look taller and skinnier, or flatter and wider. Now, just to keep things simple, we're going to set k to 1 for most of this. Because the real star, the true shapeshifter, is that little a up there, the exponent. Just changing this one number is what completely transforms the graph's entire personality. So, let's do it. Let's start playing with that a value. We're going to start with some numbers we all know and love, positive whole numbers, and see what kind of shapes they cook up. Okay, case number 1. What happens when a is a positive, even number? Like 2, 4, 6, and so on. Well, the most famous one of the bunch is x squared, and it gives us this absolutely beautiful, symmetrical U shape that we call a parabola. And what's cool is that all of these even-powered functions, they share the same family traits. If we check out their properties, their domain, that's all the possible x inputs, can be literally any number you can think of. But their range, the y outputs, is always 0 or positive. You can see it right on the graph. It never ever dips below that horizontal x-axis. And the big one? They are all perfectly symmetrical around the y-axis. It's like a perfect mirror image of itself. Now, let's change things up. What happens if a is a positive odd number, like 3 or 5 or 7? The whole graph just completely transforms. That U shape is gone, and instead we get this elegant, twisting S-curve that snakes its way right through the center. And you guessed it, their properties are totally different too. Notice how now both the domain and the range are all real numbers. This graph just keeps going forever, up, down, left, and right. And the symmetry has changed. It's not a mirror image across the y-axis anymore. Instead, it's symmetrical about the origin, which is a bit different. It means if you could put a pin in the very center and rotate the whole graph 180 degrees, it would land perfectly on top of itself. Pretty cool. Okay, so we've seen what positive whole numbers can do, but what happens when our little shapeshifter a gets weird? Like, what if it goes negative, or what if it becomes a fraction? Well, this is where the graphs start to break apart and bend in some really new and unexpected ways. So when a becomes a negative integer, like -1 or -2, something dramatic happens. The graph literally fractures. It splits into two completely separate pieces, creating this shape we call a hyperbola. It looks like the graph is trying to get as far away from the center as possible. So why does it break like that? Well, you got to remember that a negative exponent, like x to the power of -1, is just a fancy way of writing 1 divided by x. And there's one golden rule in math: you can never, ever, ever divide by 0. It's forbidden. So that's why x can't be 0, and that's what creates that physical gap in the graph. The curve gets infinitely close to those center lines, the axes, but it will never actually touch them. We call those invisible boundary lines asymptotes. And for our last case, what happens when a is a fraction, a rational number, like 1/2? Well, an exponent of 1/2 is just another way of writing the square root of a number, and this gives us the very familiar shape of the square root function, which, if you look at it, kind of just looks like a parabola that got tired and fell over on its side. So let's just step back and take this all in. We've got a U-shape, an S-curve, a fractured hyperbola, a sideways curve, all of these completely different shapes, all coming from just tweaking one single number in one super simple formula. It's really kind of amazing, isn't it? That power function formula, f of x equals kx to the a, is basically the source code for this incredible library of shapes. And by changing the exponent a, we're just telling the code which shape we want it to draw. It's just a perfect example of how beautiful and elegant math can be. So the next time you're out and about and you see the curve of a bridge, or you think about the path of a planet, or even the shape of a cooling tower, ask yourself, could that be a power function doing its thing? Now that you know the code, I promise you, you're going to start seeing these shapes everywhere. So what are you going to find first?